developing the analysis of the finite element method. So he has his hands in both communities and also spent time in industry. So look forward to your talk.
Thank you very much. So I apologize that I'm not standing, but I have a problem with my hip. That's why I walk with two crutches. And on the weekend I walk too much and I got a cramp in my right leg. It's not completely gone, so I don't think I can stand the whole time. So please excuse this. So yes, what I wanted to do is give a foundational talk now. And foundations in the sense is what we need, what we want to, and it came up during the workshop a couple of times, that we're going to need probability measures on infinite dimensional spaces. And that's the first talk. In contrast to what the abstract says, I'm going to rearrange the things and talk about the second part first part second, okay? And so the first part I will talk about what's called weak measurability and weak distributions, and that's one way of circumventing this difficulty. So let me just give you a little overview. So I'll tell you a few of the challenges which exist and which are difficult. So somehow probability theory and analysis are not always compatible, and it's difficult to make them compatible, especially in this infinite dimensional cases. And so one way of doing this is what's called weak processes or generalized distributions or weak distributions and so on. And then the second part of the talk will be another approach to probability theory, which really came up historically in the development of quantum theory, but it was about 10 years, a little bit later than Kolmogorov. And that's why I never caught on. But it's used in physics and quantum theory and quantum field theory and so on. And it allows, that's one thing what it does, it allows to deal with random variables which are not commutative. This is important in physics. If your observation influences the object you're observing. So that'll be the second part of the talk. So let me go to challenges. So as you've seen, we formulate some of the models we want to do uncertainty quantification with, or we want to use to do updating, whatever. They're formulated as partial differential equations or something similar. So these are equations in infinite dimensional spaces, in function spaces essentially. And so the simplest of such spaces is a Hilbert space. By the way, so is everyone comfortable with these notions? Hilbert space, dual space, sigma algebra, and all that? Yeah, okay. Please call out if you want to. I'll do a 5-minute think of what's important about this so you understand the rest of the talk. But it's not necessary.
I would find it useful.
Okay, I'll do a few remarks there. Okay.
I know
So,
Hilbert space.
yeah, I'll do this on the blackboard. So you all know the Euclidean space Rn with finite dimensional coordinates, and then we have the Euclidean norm, which is just the sum of squares. Okay, so if x is a vector in here, so then we have sum of xi squared, it's called the norm squared of the thing. Okay, and it actually comes from an inner product, which I'd like to write like this. Okay. So the inner product of good itself. Now we'd like to carry this over to the case when this n is infinity, okay, countable infinity to make it first. Okay, so then of course this sum doesn't have to be finite always. Okay, so this space is called little L2, and that's the space of all infinite sequences. Such that the sum of squares, now goes I goes from 1 to infinity, is less than infinity. Okay? So it's not all sequences, but the sum of squares has to sum with something smaller than 1. So another important concept is what is a dual space. So formally it's the space of, so if X is a vector space, then the dual space, known as X star, is the space of all linear maps of X to the underlying fields. Typically real numbers or complex numbers. And that will, so this gives us access to what's called duality, and there's a lot of things which can be done with duality, and it's used in many, many cases. Okay, so we'll see a few of these things right now. And the other thing we need is sigma algebra. So when we want to put a probability measure on certain subsets of a space like that, it turns out, unfortunately, it's deep in the foundations of mathematics, it's not possible to do this for all subsets. Okay, and so a certain number of subsets have to be picked, and in a space like this here, where there is a topology is a structure which allows you to say whether the sequence converges or not. So it defines what neighborhoods are and whatever. So neighborhoods in this case is everything around a point where the norm is less than some number. Okay, and so these neighborhoods generate, if you want to, you can define with them what are open sets. Open sets are sets without the boundary, so to speak. They're fuzzy at the boundary. And so each point has still a neighborhood which is inside the set. And then you can, so these sets you'd like to be able to assign a probability measure. And, but that's not enough, you need a bit of structure, like the intersection of two sets, you still want to assign a probability measure, and the complement of a set too. And something with that structure is called a sigma algebra. Okay, so that's not all subsets of this, but just a certain number. Now, if we have a probability, so we have an infinite dimensional space, let's say a Hilbert space, like this one here, we call it H. Okay, and we have a random variable, which is H valued. Okay, so this is what we're interested typically, and let's say something about it. So there's some probability space, let me call it omega, and a mapping R into H. Then we typically, by the way, so this is typically how random variables are defined, but then when you work with it, you realize you actually never ever see the space. And that's funny somehow. So one of the reasons we'll see why this is funny, okay? So typically, you're only interested in what's called the distribution measure on this space. So here we have a measure, let me call it P, okay? And what we're interested here is how this measure is pushed forward there. So it's called the push forward measure. I'll write it like this, okay? I'll not define it now, but it actually means, so you take the sets generated by the open sets, this is called the Borel sigma algebra here, and then every inverse thing here, has, that's the measure you give that thing there, okay? Good, and unfortunately, like with Hilbert spaces, there are difficulties appear, okay? So it's not possible to do this like it is at 5 dimensions. That's one of the basic difficulties. And you might have seen this in the talks where people actually wrote this down. And we will come to this in a second. So if we're in an infinite dimensional Hilbert space, the first thing which we miss is what's called the Lebesgue measure. So that's the measure we have measuring subsets in a finite dimensional space, which is invariant against translations. Okay. There is no such measure on an infinite dimensional space, unless you have the zero measure, which I exclude now. Okay, and that's, so the first problem comes, we cannot write densities like we do in the finite dimensional case. Because densities are typically with respect to the Lebesgue measure as the background measure. Okay. Then if there isn't any, we can't write densities. That's number one, the probability. The second one, which you'd like in the Euclidean space, is we know in the Euclidean space the norm doesn't change if we just rotate. Okay, so you'd like things, also probability measures, which are invariant under rotation. For instance, especially the Gaussian measure, which is equal variance in each direction. Okay, and again, such a measure is not possible on a Hilbert space. So that's what I call the iso-Gaussian measure. This is what you would call white noise. White noise is not possible on a Hilbert space. Okay. But on the other hand, we need, so this is, in my view, an extreme, or not extreme, an ideal object which we need for many things we want to compute. I mean, after all, we're here in Cambridge. This is what Paul Dirac was, and in the building where our offices are, there's actually a bust of Paul Dirac. We all know Dirac invented the Dirac delta. Okay? said he needs a function, he called it, it turns out it's not a function, but he needs an object which acts in a certain way. And it took mathematics like 20 years to actually figure out what it really was. Okay, similar with white noise. So we need things like this. And then the second part, this is this other approach to probability theory, which, yeah, in my view, I may say it, I have said it at the end again too, has two last points about this. The normal one using sigma algebras and measures is in teaching, I find it's very difficult to teach young students sigma algebras and measures, and it's easier to teach random variables and expectations, which are averages. Okay, this is what this builds on. And on the other hand, it allows this extension to non-commuting random variables. So this becomes important, for instance, if you deal with random matrices and things like that, or random tensor fields or whatever. So things which have an algebraic structure. Looking at my random matrices or random tensor fields, you're typically interested in their eigenvalues and how they're distributed. So these things depend on algebraic properties. So you have to take this into account. Okay? And then I'll just sketch how Bayesian theory can be done in these cases. Okay, so the outlook will come. So one thing we'll see is weak processes or weak distributions can be used, and tensor products appear naturally. So we've had a talk in the workshop on how tensor products can be used to actually have a very sparse, what's there, low rank approximation of all these things. So we can deal with huge objects, which if you look at all the components, there's more components than there's elementary particles in the universe, and we can still deal with it, okay, in this way. So this is where it really comes from. And the other thing I was also already saying, so instead of sigma algebras and probability measures, we'll use random variables and expectation as the basis. I'll just sketch on how this works. So this will be very, very superficial, I have to say, the talk, so I will, please don't expect to see any details now, okay? So I'm just trying to give you the idea, okay? And it turns out between these probability algebras, as they will be called, and spectral theory linear operators, that there's a very, very close connection, okay? So I'll hint at this too. And the other question is, how can we deal with really wild random variables? So wild is in quotes. So something, for instance, like functions, and the Dirac delta and its derivative and second derivative, whatever, we know how to handle this in the normal case. How can we do the same thing with random variables? It turns out, yes, we can, okay? And I'll just hint at how this is, and then I'll say a little bit how Bayesian updating looks in this setting, okay? And about the last part, I will really not talk anything. You'll see it. People who do Galerkin methods, they know that this duality, whatever, this is all formulated in duality, and that this allows to use Galerkin methods. That will not go really into this. Okay. So these weak distributions is what do we want? So we want a probability of infinite dimensional function space, and let's assume we have a probability space, which I call omega, and with probability measure p. A is the sigma algebra. So these are the subsets of omega which are measurable, which we can assign a probability to, okay? And the probability is just a positive measure, and the number assigned to these sets is between 0 and 1, okay? Where the whole set gets the number 1, and the empty set gives the number 0, okay? And so we'd like to have this map measurable, as I've written down there, and that's the problem, okay? So the push forward, if this is possible, the push forward would be a measure. But that doesn't work always, okay? This you could call a strong distribution, but it doesn't always exist on infinite dimensional Hilbert spaces, okay? And when you really look, it turns out that it's not really needed. Okay, what is really needed is, maybe I can do it here. Can you see this little thing here? So then I don't have to point around here, okay. So what is really needed is that you look at the dual space, okay, in this case of a Hilbert space, it's the space itself, okay, and then you look at objects like this. So you take the inner product of the fixed object with this random variable, okay, and that's just a normal random variable, a real valued one. And that one you want to be a normal random variable, to be measurable, and that's enough, okay, because the conditions we have these on this infinite dimensional object You have to see this infinite dimensional object. It's nothing you will ever see. It is an ideal thing in mathematics, but you never ever see. And all we need is its finite dimensional projection. So this is the simplest finite dimensional projection in a way, okay? And that's enough, because all conditions we formulate on what this R, or functions on what this R depends on. So this R may be an input to an or partial differential equation, and the solution of the partial differential equation living in another infinite dimensional space has to satisfy something. The conditions it has to satisfy, we can write in a weak form. So it can be formulated in this form. Okay, so that's why that is enough. Okay, good. And then in the end, we want to make, so what do we want to do by what do we want to do basically when we do uncertainty quantification? In my view, it's two things we want to do. One is to decide something. Okay, for this we'll typically take an expectation of a function of whatever the state of the system is. And if it's this way, then we say, we do it, so we do something or we don't do something. Okay. Let the truck go over the bridge or something like this. Let the nuclear power plant operate or whatever. So it should be based on something like this, not always is, but the idea is this is how you take the decisions. And the other thing we want to do is updating knowledge. Okay, so this is Bayesian theory. So these are the two things. And again, so these things you take a decision on, they can again be a finite dimensional. You're not going to look at infinitely many variables to take a decision. Okay, so that's why that's enough. Good. So let's just write down for an infinite dimensional space what I just wrote down what I know. Again, I'm not a specialist really on this. So we take an infinite dimensional space and call it Z now. We allow it to be not just a Hilbert space, but a broader class called local convex spaces. Okay, it includes Hilbert Banach spaces and spaces of distributions and things like this. Okay, and we like the law of R to be a probability measure. Okay, the push forward. So the first thing it turns out, for this to be measurable, Z has to be separable, which means there has to be like the rational numbers and the real numbers. There has to be a countable set which is dense in the whole set. Okay. Now, in some cases, this is the case. Okay, the separable spaces are Hilbert spaces with a countable cons means complete orthonormal systems, or a complete orthonormal basis. Okay. Then the spaces of continuous functions with k derivatives, the functions with have p's moment, you could say, in probability theory. Okay. Where p is between 1 and less than infinity, and then the ones which have k derivatives, and all k derivatives have a p's moment. Okay, so these are spaces which appear in analysis. Okay, but not separable spaces are, for instance, a Hilbert space with an uncountable complete orthonormal system, or it's an important space L infinity. For instance, if you remember, quite a few people talked about the diffusion equation and the coefficient, the diffusion coefficient being a random object in there. Analytically, that lives in the space L infinity. But L infinity is a non-separable space, so a problem appears there, okay? And little L infinity, it would be that one, with the numbers bounded, okay, is also not measurable. The bounded variations are not separable, not separable. Then the Hölder spaces are not measurable, not separable. Then the ones here with infinity. An important thing, the space of all linear operators of one infinite dimensional space into itself, let's say, are also not separable. Okay. And then if we go back to the case of Hilbert space, so for a measure to exist on a Hilbert space, the covariance operator of that measure has to be what's called trace class. Okay, so you look at the eigenvalues of the covariance, and the sum of the eigenvalues has to be less than infinity. It has to be infinite. Okay. That's what's called a trace class operator. The trace will be the sum of the eigenvalues. Okay, and another word is nuclear. Okay, nothing dangerous here. It comes from integral equations where these objects were the kernel of the integral operator. So another word for kernel is nuclear. So that's where the word comes from. Okay, and for the if you have it on a separate Banach space, the norm has to satisfy certain things if you do it. Another way where you can do it is on duals of nuclear spaces. Okay, I will not explain what this means. So there's a few situations where we can define measures, but not in all the cases we would like. Okay, Good, let me just start an introductory example. So let's assume we have the finite dimensional setting as I wrote down here, and we take n IID standard Gaussian, means they're independent and they have mean 0, variance 1 random variables, and then look at this random vector, okay? So, and then for any h in this Hilbert space, I can now take the inner product between h and this random variable. I hope you all realize this is a linear thing in H, okay? And it defines a mapping from the space H into the space of random variables. And it turns out this is a random variable, which is, again, 0 mean, and variance is norm of H squared, okay? So you all see it is invariant under rotations, because we know the Euclidean norm is invariant under rotation. So this is an iso-Gaussian probability measure. This is white noise on a finite dimensional space. For me, white noise is something where the covariance is the identity, okay? Just like the delta function is the identity in some way, okay? So there's very close connection between these two things, okay? So we realize that this mapping, R is a map from H to the space of Gaussian random variables, okay? And, well, we can actually introduce a inner product on the space of Gaussian things by just taking the expectation of the product, okay? And then the covariance is this here, it's R star R, okay? That's a very, everyone knows this, and we know a Gaussian measure is completely determined by this, and the mean is 0 here, so we're not doing anything in the mean. Now, if we have an infinite dimensional Hilbert space, this is not probable. For instance, if I take infinitely many IID 0, 1 Gaussian variables, and I put it into an infinitely long vector, then with probability 1, this guy is not in L2. So it's not something we can really use. And this is the problem, okay? But I can still define a mapping, okay? So this means a linear mapping from H into the space of, which is spanned by the Gaussian random variables, okay? And I take one of the unit normal orthonormal basis vectors, and the nth one I map on the nth IID noise here, okay? So I assume this Cn are independent IID noises, they span a space, okay? And I just map the basis vector on here, and then the mapping is completely defined. If I say what it does on the basis, I can extend it by linearity, okay? So this map can still be defined, and then when we take an object H and then map it, it turns out it also has this distribution. So it has as if it was an iso-Gaussian distribution, although it's not possible to have one. So with this kind of map, I can introduce one, okay? Although the mapping from the X's into the Hilbert space is not measurable. But the combination with the inner product here is, so that's what's called weakly measurable, okay?
It depends on the sigma algebra that you put. You have to put a cylindrical sigma algebra.
Yeah, so I assume on the Hilbert space, the Borel sigma algebra, yeah.
No,
On the X's, it's the product sigma algebra. So it's a product of one-dimensional spaces. That's the product sigma algebra.
yes, and if you restrict to the cylindrical sigma algebra.
Yeah, but they're not necessarily a sigma algebra. Yeah. So we can talk about the details. I think we'll confuse everything in this time talking about cylindrical sigma algebras and so on. So it is not possible to put an iso Gaussian measure on a Hilbert space. Okay, it's not possible. And I just hinted why it's not possible. So it's not a proof, but it's just a hint. I want to prove this. Okay, and viewing it in this weak sense, it is possible to work with objects like that. All we need is this mapping, capital R. Okay, good. In case maybe you know better, and it's easier to look at. Assume this is a standard Wiener process on the unit interval. Okay, I hope you all know this. Okay, so we look at the space which is spanned by these random variables. Okay, this is a Gaussian Hilbert space. They all have mean 0. Okay, and the inner product is again the same thing as before. Okay, and then so how is Wiener measure introduced on the continuous functions? It's also introduced in this weak sense. How is it done? Oh, this C with a little bullet down here means the continuous functions which start at 0. 0 there, 0. And so how's it done? We define a linear map from here. So we take a continuous function and then we compute its E2 integral. And of course, that's a Gaussian random variable with mean 0. Yeah? So it's exactly this kind of linear map. And that's how the Gaussian measure on the space of continuous functions is defined. So it's what I'm trying to say, it's something you know already. Okay? So all the both concepts I'm talking about today are not new. Okay? So you know them, and we just have to see them in a different light and start using them, I think. Okay? And then this E2 integral we can extend to step functions. So step functions are on one part of the interval from 0 to t, and then they drop to 0. Okay? So I take all linear combinations of step functions. That's this here, and I map it onto this. So this is a Gaussian random variable. So I have a linear map from the space of step functions to Gaussian random variables. And it's easy to see that when we take the L2 in a product here, this map does not change the length of the vector. Okay, so it's an isometry. And it can be extended from the step functions to the whole space L2 because the step functions are dense in this space. So it's a continuous linear map that can be extended to the whole space. Okay, and it's exactly this mapping R we're talking about before. Okay, so what you see that the Wiener measure is defined in this way. Okay, I've never ever seen someone defining it in any different other way. Okay, although you can show C is one of these spaces which has a rather defined norm, and you can define a measure on its Borel sigma algebra. Okay, but not on L2. So this way we've extended the map to L2. But it's not possible to do that, and we still have something which looks like an iso-Gaussian measure. Okay, so this map is more general than this random variable. Okay, and the thing is to not insist on having a random variable like that. All you need is this linear map, capital R. Okay, good. So and then if we have a measure, of course, we can define the covariance. Okay, which is this here. So covariance is a map from this space to CV, and it satisfies this thing here, okay? So the little dots in here, this is what you're doing the expectation over, and the V and U are two vectors, and it has to be this. So this is the inner product of the Hilbert space, okay? So the covariance turns out to be R star times R. R star is the dual operator, the word matrix, the transposed conjugate complex, which maps backwards, okay? And one has white noise again if C is the identity, okay? But one can show on a Hilbert space that's not possible. So a measure on the Borel sigma algebra exists only if C is trace class, okay? And the identity is not trace class on an infinite dimensional space. It's infinitely many ones, they don't sum to anything finite, okay? So again, I've said this already too, so in some cases it's possible, in some cases it's not. So what is a weak probability distribution? So it's a map from the dual space into a space of random variables. That's what's called the weak distribution, okay? And then this would correspond to the case, if we have a map like this, it's called weakly measurable, okay? Good, so that's the idea. And this is actually, this idea, although I think it arose in stochastics, is something which you can use even in a more general sense. If you have a parameter-dependent mapping into some high-dimensional space, then you can rip somehow the two things apart, the thing being in a high-dimensional space and the parametric dependence. And this is what we're trying to do here by having random variables times something which is in the infinite dimensional space. And this will lead to tensor products, okay? So assume we have a general set P, doesn't have to be a probability space, okay? And we have a mapping from P to some space Z. We'll again assume it's a Hilbert space, or the subspace where all these things lie is a Hilbert space, okay? To make it simple. And we want, so often we need other representations. P may be the parameters where you have a probability, whatever, in your problem, but P may not be. I mean, most of the things we saw here in the workshop, P was assumed already to be some subset of Rn. So someone's already put parameters on your situations. But P is many different things. It's what the weather was yesterday, I don't know, or whatever influences your problem. So this is what P is. And the first thing you have to do is typically put coordinates on this set. So this is a kind of parametrization, and this is how you can do it. Coordinates are actually real valued functions on the set. Okay, so this is what coordinates are. And if there are enough of them, it defines exactly one point in the set. Okay, good. Again, to such function corresponds a linear map. So, okay, into the space of functions from P into the real numbers. Okay, and this is exactly the same situation as we had before. Before these were random variables. Okay, now it's more general. And by construction, this map is injective. I can use this to carry the inner product from the space U over here to the space R, okay, on the image of this thing. Okay, it turns out this map is unitary, and this case space again is very well known. It's called the reproducing kernel Hilbert space, okay, because it's the space of functions on the set P, okay, and the kernel looks like this. It's the inner product of this map with itself. But in contrast to P, which was just some set, this set R is a vector space, so it's much easier to deal with. Okay, that's the reason of doing it. Okay, so just a little excursion to show the connections with reproducing kernel Hilbert spaces. So the kernel was this, I said already, and you can see we can recover the set because this is just the linear combinations of these functions. Okay, and it's easy to prove it has this reproducing property. So we take any function on the set P, which is in this space, and take the inner product with the kernel at some point P. It gives me the value of the function at that point P. It's called the reproducing property, okay? And I will not go into the second part. You know, this is used in machine learning and classification things and so on, okay? Good, so some examples. A z-valued random variable, that's what we had before, or a function describing maybe an equation or a solution from something which depends on the parameter P and so on. Okay, so these are all cases where you have something from a parameter space into some vector space. Okay, and they can be all dealt like with this. Okay, so an example, for instance, you have a random field, and what would it be? It would be some kind of spatial average. So we map the U, which is a function of space. So remember, X is space. This is the random field. We take a certain spatial average, okay, which gives us a real number. So this would be this mapping capital R. Okay, and then we can define what the same thing with correlation is, which is just R times R. Maybe one more thing. So what I had before in the reproducing kernel Hilbert space, the inner product on the reproducing kernel Hilbert space come from the original space. But often on this space of functions on my parameter set, I have another measure of what's important, another inner product. So the inner product, the idea is we'll give a big norm to a function which is important and a small norm which is not important. And let's call this inner product Q, sorry. So let me call it Q, okay? And now I can define the adjoint with respect to that, okay? And that gives me what I call here the correlations, again, something like the covariance. In case this measure comes this inner product comes from a measure, then it looks like this. Okay. What I know now, this guy is self-adjoint in positive definite. That's the important part. So I know it has a real spectrum on the positive real axis, and I can write down the spectral decomposition. So different ways of writing this in infinite dimensions. Okay, that we have the problem of continuous spectrum appearing and so on. One way of writing is what you know from matrices. You write a unitary or orthogonal matrix times a multiplication by a diagonal matrix. In this case, it would be multiplication by a function. And again, the vectors form. Okay? Or you can write it like this. So this is what you know from finite dimensions. Unfortunately, we have sometimes a continuous spectrum, so the sum has to be an integral. Okay? I will largely skip this part here. That's not important for what I want to tell. Okay? So we can write the C of U. We can write it like this. Okay, C applied to a vector U looks like this, and what you see here is tensor products appearing. Okay, this is where they come from. Okay, and there's another way of writing it. So, what the important thing is to remember that C is the product of two very similar operators. Okay, it's R star R. Okay, and I can do this for a spectral decomposition. I can write it like this here. It's again like R star R, but now it's on the spectrum. So I can use these decompositions of this operator to do parameterizations, okay? Especially the one with the spectrum leads what's called the single value decomposition, and what everyone knows as the Kolmogorov expansion, okay? So I can write the R, it turns out, as this, where the S's are defined this way, okay? And then the KLE, Kolmogorov expansion of this random element, is just this, okay? And you see now it's become linear in this new parameters SA. So the thing is, and that's the nice thing about this. Okay? And so if I rewrite this in different, you see this is a tensor product. So tensor product appearing. I've separated one influence from the other one. Okay? This is what this does. Okay? So there's many different ways of factorizing. It turns out every parameterization corresponds to factorization, and every factorization corresponds to a parameterization. Okay? In finite dimensions, I'm sure you all know the Cholesky decomposition of the covariance, and doing it with that one, that's one of these. Okay? Sorry. Okay, good. And then, of course, you can not just do it with R star R, you can do it with R star, and those are on the reproducing kernel Hilbert space. They are used as integral transforms. Okay, so I'll not go into this part here. Good. So, sorry. Okay. So what we allow, so this allows us to choose different representations for our object, what we're interested in. And the reproducing kernel Hilbert space, the spectral one, the Kolmogorov one, or any other one, they all look like this. There's a one-to-one correspondence. Okay, and you can choose or what's good for you or what not. Okay, so this is how you can analyze these weak distributions as well. So we have a covariance separator, and it can be analyzed and things like that, and looked at it this way. Okay, so this is all I want to tell about this part. So the points to remember are: weak probability distribution is defined by a linear operator. That makes it much more accessible as a random variable from omega to h, which can be anything. This is a linear operator, and then we have a lot of machinery to work on. Okay, so this is what makes it much easier. Okay, and so it's more general in infinite dimensional spaces. Okay, and I hope I've just touched on how these things we know, the singular value decomposition, Kolmogorov expansion, whatever, they come from this concept. Okay, how they're connected to this. Okay, so again, each factorization corresponds to representation the other way around. Another representation would be just to take another probability space, which has the same distribution. Okay, so often there's a good one and there's not a good one. So you can see this is like choosing a coordinate system when you do some computations. Some computations are good in Cartesian ones, but are good in spherical ones, other in cylindrical ones, and you choose the one which is appropriate. The same is true here. Okay. Good. And I've shown also you can make this mapping so that the correlation or covariance is the identity. So we can deal with white balls. Okay. Now let me come to the other part, and this is this algebraic view on probability. Okay. If we look back at the beginnings of probability theory about 500 years ago, three of the influential mathematicians are written down here. There's Jacob Bernoulli, who wrote a very influential book, and then two of his nephews who dealt with this. And when you see, I mean, of course, they didn't write down any formal definitions, but they dealt with probabilities and with random variables and whatever. And when you see how they worked on random variables, you could add random variables to each other. Okay, you can multiply them by numbers. You can multiply a random variable by another random variable. Turned out the constants were seen as some kind of degenerate random variables. Okay, and then they had something, the expectation or average or whatever, I don't know what they called it, and this turns out to be linear. Okay, and positive. A positive random variable has a positive expectation. Okay. Now, if we translate this into modern language, A and B means the random variables form a vector space. Sorry. C means the random variables are an algebra. So an algebra is a vector space with a multiplication. Okay. D means there is a existence of a unit. There's something which is sort of constant. It doesn't change. So we call a unit in the algebra. You multiply with that and nothing changes. Okay. And then the expectation, today we would say it's a positive linear function. Okay. But just to remember what is an algebra is a vector space with a multiplication which satisfies this distributive law in this case. It's an associative algebra. Okay. And then we have an identity, I will call the identity E. You multiply with the identity and nothing changes. Okay, that's what the identity is. Good, so let's think of what is the classical definition of what is a random variable. This is a la Kolmogorov. So a random variable is a measurable function from one probability space into another space with a sigma algebra, which is measurable. Okay, and then you can define a measure on the original space, and this you can use to define expectation. But the basic thing is the space, the sigma algebra, and the probability measure. Okay. Now, algebraic random variable turn out to be an element of an algebra. Okay. We want it to be unital, otherwise it's not a probability algebra, it turns out. And we need a distinguished positive linear functional. It's called the state. This call comes from physics, so that's the state of the world, so to speak. Okay? And the state of the world determines what you can observe. The random variables they call observables. Okay? And you may call it expectation. Okay? And the events, which are defined by elements of the sigma algebra here, will be defined by things which we will call projections. Okay? And so this is what we're going at. Okay, so let me give you two examples of what are probability algebras. I'll start with a non-commutative example right away, the n by n matrices with complex entries. Okay, and as distinguished linear functional, I take the trace divided by n. So the identity element, of course, is the identity matrix. The identity matrix, we want it to have expected value 1, and this will do it here. Okay, it sums n ones and divided by n. Okay, and of course the diagonal matrix is a subset of here or subspace. That's a commutative algebra. Okay, another one which is probably more closer to random variables, just take simple random variables. So we take the functions which are 1 on some set which is in the sigma algebra, and then we take the space spanned by these. So this is the space of measurable step functions. Okay, linear combinations of these. So the unit one is of course function constantly 1, and this distinguished linear function of course is the integral. Okay, which is easily computed like this. Okay. The question is now, for instance, of course, probability theory exists. I don't want to do away with the idea of measure, whatever. So how are these two related? Can I recover probability from this expectation? Well, yes, I can. So the probability of a set is just the expected value of this guy. And this guy turns out to be a projection, if you look at it. Okay? So it's easy, once you have expectation as an operator, it's easy to define what a probability is. Okay. For the ones who are not too familiar with abstract algebra, so these are things, easy things, you can just think of matrices. Okay? So for any matrix, I can define any power of the matrix. Some of them are invertible. Okay? And they're invertible if this equation holds. That means I can define polynomials and matrices. Okay? Then we call, and I have to say also, so we have this algebra, and I have to embed it into a complex algebra for the theory to work. And some French mathematician, I don't know whether it was Hermann or Legendre, said the truth, the path between two real truths often goes through the complex plane. Okay? And that's true here too. I have to embed this here into this complex setting. In the end, I will be only interested in self-adjoint elements of the algebra. These are the observables. The others are only there to make the theory work. Okay? Good. And so we have a star operation, which is like taking the transpose in matrices, okay, and conjugate complex, and it satisfies these equations. In our little example here is just taking the conjugate complex of the coefficients, and for matrices is taking the transpose and then doing conjugate complex. Okay, we call the algebra abelian or commutative if A times B is the same as B times A, and we write the difference here as A comma B. That's called the commutator. Okay, these three things, I think we just skip this just to make all the operations continuous. Okay, so but don't worry about this part right now. Okay, so just a few examples of abelian algebras. I put John von Neumann's picture here. He has very different names. So he was born in Hungary, and then was János Neumann And he went to Göttingen in Germany, and he called himself Johann von Neumann. And then he went to the US and called himself George von Neumann. And he worked quite a bit on these algebras, okay, in the development of quantum theory. Just have a look at a few algebras so you see there's some of these things it gives. For instance, all random variables together. So all the measurable functions, they are an algebra. You can add them, you can multiply them by numbers, so they form a linear space. You can multiply them with each other. The product of two measurable functions is measurable, so they form an algebra. Okay? We don't have necessarily a function on all random variables. They'll have to restrict later on. Okay? Or we take the continuous functions. Okay? They're actually a C-star algebra. Okay? Or like the random variables with all moments. Okay? The essentially bounded ones, an important class. Okay? Vectors with a Hadamard product, that's a pointwise product. So this is in MATLAB writing dot times between two vectors. Okay, but that's in commutative algebra. Polynomials and M variables, which commute. Okay, and of course Wiener's polynomial chaos. Okay, so these are polynomials in possibly infinitely many variables. These random variables. Okay, and they form an algebra. The product of two polynomials is a polynomial. Okay. And we actually have an expectation operator too. It's the first coefficient of the expansion. Okay? And generalized polynomial chaos, of course, too, is an algebra. Okay, now a few non-commuting ones. We had already the matrices. Okay, we can take matrices with random variables as entries. Okay, or you take all bounded linear operators on a Hilbert space. Okay, we can take the compact linear operators. Two important ones for quantum theory is the tensor product. By the way, this is this can be written as a tensor product. It's the symmetric tensor product. And that's what physicists use to model bosons. Okay, where the Pauli exclusion rule doesn't hold. So certain elementary particles, there can be only one particle with this quantum state. And these are called fermions, like electrons and things like this. And there's other ones, there can be many in the same state. And of course, they follow different statistics. One's called the Einstein-Fermi, Dirac-Fermi statistics, I think. The other one's called the Einstein-Bose statistics. Okay, so they're both different from the Maxwell statistics. And the other two, and the space of all these tensor products called Fock space. Okay, and this would be for the fermions. Okay, good. Now again, if you think of matrices, you all know all of this here. So an element which commutes with its conjugate is called normal, okay? And where the inverse is equal to the adjoint, it's called unitary. If it's equal to the adjoint, it's called self-adjoint or Hermitian, okay? Just in matrices. So these are the observables, these are the ones we're interested in, okay? In some way they have real values. We'll see how this comes in a second. For instance, in our space of simple functions, the ones with real coefficients. Okay, an element which can be written like this: b star times b. We call that positive. Okay, and we can define the square root. This is the c here, and we can define the absolute value of a b. This is just the square root of b star b. Okay, and so we can say something is positive. Then we can define an ordering. Defines a cone, and a cone defines an ordering of these elements, okay? And positive elements which multiply with itself, give itself, these are called projections. Matrices, they would be called orthogonal projections, okay? And so it turns out they generate the whole algebra, okay? And the characteristic functions, just these guys, these are projections. Okay? Good. Another thing we need is now the thing to introduce the expected value. And it turns out that something in the dual space, the space of all linear maps from the vector space I'm dealing with into the real numbers or complex numbers in this case, okay? So we call this, the physicists call this a state, that's what it's called, okay? And it has to be positive, that means on elements like this, it has to be larger than 0. And if something's Hermitian, we want it to be also real, okay? And then we call it also Hermitian, okay? And on the unit it gives 1 and so on. That's what we call a state. Okay? And if this is 0, only when the thing is 0, we call it a faithful state. And if it satisfies like this here, we call it a tracial state because the trace of A times B is this trace of B times A, they're both square matrices. So that's what's called a tracial state. Okay. And extreme point, it turns out it's a compact set in the unit ball of the dual space. If you look at the extreme points, and the extreme points are called pure states. It's something like delta measures in the space of probability measures. Okay. Extreme points of this set of all probability measures are delta measures. Okay. And what we also need weights. So these are states which are also multiplicative. Okay, phi times A times B is phi times A times phi times B. Okay, that's typically not true for the expected value. But for these weights, we want it to be possible. It's a generalization of eigenvalue. Okay, if we have a matrix and an eigenvector, then this guy here would be a state. It would be exactly the eigenvalue. Okay, so this is what you have to think of what a weight is. It appears all the time if you do representation theory of groups, Lie groups, and so on. And then weights come up. Okay, good. And so where are we going from here? What is what we want? So I want to finish up now quickly. One more thing we need is the spectrum of an element of the algebra. Okay, and a spectrum is something, a number, a complex number, so that this guy is not inverted. Okay? Well, this is the same way you define it for matrices. Okay. And it turns out if A is self-adjoint, the spectrum is real. If P is a projection, the spectrum is either 1 or 0. Okay, so only these two elements. Okay. It's like an indicator function. Okay. And if we have a faithful state, it defines an inner product. Okay. So we can define an inner product A times B. I have to take the star here because this is all in the complex domain. So it has to be assessed with linear form. Okay. Then I can complete the algebra in this topology, and that's what's called the L2 state on the algebra. Okay. Then I can take the absolute value, which I defined before, take the pth power, take x expected value, and then one is pth square root. Okay. And then take the closure of A in this norm. Okay, and it gives me all the LP spaces. And L infinity can also be defined. I'm not doing it here. Okay. So we can view these A's now as random variables. We only care about the self-adjoint ones. The others are only there to make the theory. Okay. And we call this functional the expectation. When the world in state phi, this is what you can expect from your random variables. Okay. And when the state changes, then you have to do conditioning. Okay. We'll come to that in a second. And the projections can be seen events because the expected value is between 0 and 1. Okay. And now it's very easy to formulate what means to random variables to be uncorrelated and independent. It's actually a geometric condition. Okay. So first we split it into the constant part, which is projected onto the unit, and the rest, which has expected value 0. You all know that how to do this. Okay. It splits the algebra like this. Okay. And we call two elements uncorrelated if the twiddly parts, the ones which have expected value 0, if they're orthogonal to each other. Then you call them uncorrelated. And if the algebra is generated by two elements, this is the C square bracket A1, it's the algebra generated by this element A1, is orthogonal to the algebra generated by A2, only its twiddly parts. If these are always orthogonal for all two elements, then we call them independent. Okay? And if you go back, you'll see this is also how it is for normal random variables. Okay? And observations or samples are certain weights. The weights are so that they give you an element of the spectrum. Okay? So what you observe will be something in the spectrum of this variable, okay, as an algebraic okay. Good. So what is quickly to see is what has it to do with spectral theory of operators. Typically, if you have let's start with a matrix. You have a matrix A and assume it's a normal matrix, so it commutes with this adjoint. Then I take the algebra generated by these three elements. That's a commutative algebra, okay? And that's what we'll be looking at. And this is how spectral theory is done. I can do the same thing for operators, okay? And now let me look at two important commutative algebras, okay? One is the multiplication algebra. So I take a L infinity function and I can multiply a function from L2 by this one, and I call this the multiplication operator. So MF is mapped into K times F. Okay, so that's the simplest kind of linear mapping. And all these with different Ks, they all commute with G. Okay. So the algebra here is the same algebra as these algebra of linear operators. And then it has a sub-algebra of the continuous ones. Okay. Good. So now we can define what is a probability algebra. So it's a unit-field state star algebra with a faithful state. Okay. The additions are only important when we care about topology. I will not go into that. Okay, so we already know the non-abelian one, matrices with trace, the diagonal matrices, the abelian ones are, for instance, L infinity, okay, with a norm. Venus polynomial chaos is a probability algebra. The linear operators on a Hilbert space, this is what you have in quantum mechanics, is one, okay. And what is the trace? So you take an operator rho, which is called the density matrix in physics, and this is a trace operator, and then you can actually compute the trace of the product. Okay, so this is something which is finite, and it turns out has all the things you want from an expected value. Okay, good. And I think we'll not go into the details down there. So this rho is what's called, again, a nuclear or trace class operator. Good. So now, how do we get from this here? How do we get probability measures? This is the interesting part now. For any self-adjoint ones, I'm only interested in the self-adjoint ones. The others are only there to make the theory nice. Okay, I can define, first of all, what the kth moment is. Okay, and having that, I can define now, this is the space of all polynomials in one variable. Okay, so for each polynomial, I'll define a certain real number. Okay, I take the polynomial, I put the element of the algebra in there. It's again an element for the algebra. Then I take its exact expected value. That's the value I assign to this polynomial. Okay, so it's a mapping from polynomials into the real numbers. And it turns out, I call this the law of the random variable. So if this is the same, then the two random variables are the same. Okay. Now, if I take a self-adjoint element, I claim there's a unique probability distribution which defines the law. Okay. And how do I do it? So I want to define this PA here, okay? Well, I just take the polynomial and I apply this mapping to it. Okay, that's phi of P of A. Okay, now I've defined it for all polynomials. Polynomials, if I do it right, are dense in the set of continuous functions. It turns out to be a continuous linear function on a dense subset. So I can extend it to all continuous functions, which means it's a measure. That's another definition of a measure. It's a continuous linear function on the space of continuous functions. So I have a measure this way. There exists a measure which does exactly what I want. Okay? And also for non-commutative ones. Okay? So this algebraic path completely recovers the measure theoretic one. Okay? So maybe just a few things on how, now this is a very complex sort of abstract concept. The way, what I've done it here, I've said, I require for my random variables to satisfy these kind of rules. I'll show you some examples to say that I'm not talking about the empty set. So the rules which I formulated here, they're not self-contradictory, okay? And, but the question is, now if you have an abstract set like this, and this is how quantum theory, quantum field theory today is formulated in its abstract setting. They say we have certain observables and they satisfy certain rules. Yeah? And then turn out they can be embedded in an algebra like that. How can we realize this as concrete analytic objects? Okay. So it turns out, and these are called representations of this algebra. Okay. And typically these representations are as linear mappings on some vector space. Okay. So one is when it's abelian. Then it turns out it can be represented just as continuous functions on a subset on the dual space. Okay? And this is on this what's called the spectrum. It's called the Gelfand representation. But anyway, even if it's not commutative or abelian, I can always do what's called the regular representation. Remember, I can form a Hilbert space together with this expectation function. Okay? And then each A is mapped onto a linear operator, but just multiplying with it. This is obviously linear in B. So A defines a linear operator, that's called the regular representation. So right away, I have a representation as operators on some Hilbert space. Okay? Good. So just to tell you what is known about different representations. Okay? The most boring ones are the ones where every element which is non-zero is invertible. These are isomorphic to the complex numbers. So they're not so interesting. very small somehow, okay? Then the next ones are, and this is the theorem by Gelfand-Naimark, so if it is abelian one, so UAC means a unital abelian C-star algebra, is isomorphic to the algebra of continuous functions, okay, on a compact set. And then if you have additionally a state on there, you can show it is isomorphic to L infinity on a probability space. So the abelian algebras are the same as probability, as random variables, okay? And the extension is now you can deal with non-abelian ones, okay? And they can be represented as linear operators on a Hilbert space. I will not go into the details here. And this is connected with Gelfand and von Neumann, okay? And it's still work going on there here, okay? So what are the connections to spectral theory now? Okay, we saw that each element can be connected to a linear operator, and this is the connection, okay? And actually it turns out what this set called the spectrum, it maps the algebra onto its spectrum as a subset of the complex numbers, okay? So what this means, I can use now the spectral theory of operators where something can be done with the functional calculus, so I can define what is a function of the operator, okay? First I can do it for functions which have expansion in a power series, so the holomorphic calculus, and I can do it for continuous ones, and I can do it for all measurable functions. So I can define the sign of an operator, the exponential, and all these things which I like to do. I can do now the same thing for elements of my algebra. Okay, that's a very powerful calculus. I can define all these operations on the algebra, on the abstract algebra in this way. Okay. Good. So what do we have to remember? I just want to finish up now. So all of probability theory, as we know it, as it deals with commuting random variables and measures and probability measures, can be captured by this theory. Okay, this corresponds to abelian algebras. Okay, no measure theory is necessary, but we can recover measures when we want to. Okay, plus we have the non-commutative thing, so we can deal with things like, let's say, random matrices and look at how its eigenvalues are distributed. These are distinctly algebraic things, the eigenvalues. Okay, so it's not, you can't get at it by looking at entries in the matrix. Okay, so you have to look at the whole thing. Okay, the projections generate the whole algebra. Okay, and they actually shadow, so that the intersection is the product of two, and taking the complement is taking this here. Okay, so this way you can play back between sigma algebras and these algebras. Okay, and the basic probability measure again you define as the measure of so the expected value of a projection. Okay, in my view, this view on the whole thing is actually what we're often using already, and it has also numerically, I think, consequences. So I think it's easier to work with random variables and expectations than with measures in sigma algebras. I'll tell you why I think this. Okay, so if you look at the measures from this point of view, they live in the positive cone of the unit ball in the Banach space of all bounded measures. Okay, they have to be positive, that's why they're in the positive cone, and they have to have total measure 1, that's why they're on the unit ball. Okay, and it's actually a flat set, we know that too. In a complicated set, the extreme points are Dirac measures. Okay, and now if you do updating, whatever, you have to change the measure. That means you have to push it around on this set on the unit ball. That I find numerically difficult to do. Okay, and all you get is if you discretize this, for instance, with a Monte Carlo, you can say each Monte Carlo is a Dirac measure at this point. You get what's called weak star convergence of measures. That's very poor convergence. You cannot measure how quickly something converges, things like this. Okay? Whereas when you deal with random variables, okay, they live in a vector space. When you discretize this, you can use linear algebra. We have a lot of methods to work with linear algebra, so that you can use all this too. Okay, and it goes easily into Galerkin methods and all these things. So this is why I think this is easier to work with numerically. Okay, just let me tell you why it's used in other fields, these algebras. So in geometry, people speaking now of non-commutative C-star algebras, that's called non-commutative geometry. Okay, because the set of all continuous functions on a set describes the geometry on the set somehow, how many holes it has and whatever. Okay, so it's called homology theory and cohomology theory and so on. I will not go into this. Probability, we've seen this, okay, so in quantum theory it's used to do quantum probability. And by the way, so there's claims that C-star algebras, non-commutative ones, are connected with the large-scale geometry of our universe. That somehow do this, and the W-star algebras, a subset of these are used for in quantum theory. Okay, good. Just one quick word on how to deal now with wild random variables. Okay, so if you think of the Dirac delta function, how this is, in my view, is something like when you do Far Eastern martial arts. Okay, so if your opponent is stronger than you and he wants to go this way, you don't block him. You let him go there, and then you make him fall. Okay, this is it. And here's the same thing too. So it's something complicated we work with, or in a transmitted sense or whatever. So here we want to work with a complicated. We go to something which is really, really nice, and then we use something to deal with this. Okay, so just let's think of the Dirac delta function. Okay, how do we do it? So we deal by looking at all the infinitely differentiable maps, functions with compact support. Okay, and then their duals. This is something where the Dirac delta lives in and so on. Okay, we can do it like this, or what's called tempered. This at space S. These are the Schwarz distributions, the space of tempered distributions. Okay, so how do we do it? Probability algebras. We take a nice probability algebra, which I call N, which is embedded, densely embedded in a Hilbert space formulated, which comes out from my probability algebra, and then I look at its dual thing. Okay, and it's what's called a Gelfand triplet. Okay, and so it's known how to deal with this. So this way we can deal with random variables which are not measurable functions. Okay, they're Wilder. Okay, and if you have random variables with values in a vector space where you look at the tensor product and then it's dual. Okay, good. Just what does Bayesian updating look like in this setting? Okay, so assume you have something Q. This is what you like the information on. It is part of some system where the state is U, okay, and you can observe something which depends on the state in the Q, okay, these are your observations. And you like to use this now to identify Q, okay, you know we do this via basis theory. Okay, so that's conditioning, okay. And so basis formula, I've written it down here, so this is the prior information I have on Q, and this is the, what's called the likelihood, so the probability of measuring Y, given that I of Q was true. And this is basis theorem, as we all know it. Problem is here, if I'm conditioning of something with measure 0, then I have 0 divided by 0, and it doesn't work. So that's one thing which cannot be cleared up, okay? And it leads to what's called the Kolmogorov paradoxon. And a special case is, where you can do it, is when they have a joint distribution, sort of a joint density, Y and Q. Well, then you can write this in densities, then it works. Okay, and you condition on subsets of measure 0, but otherwise you really cannot do it. Okay, so I think this functional analysis view allows you to deal with the singular cases as well. Okay, so according to Kolmogorov, by the way, conditional probability is not defined by this equation. This doesn't work, unfortunately. But you have to define it by conditional expectation, okay? And it's what we had before, the expectation of a function which is 1 on the set, 0 otherwise, that gives the probability. So now what is conditional probability? I have to translate it now. Conditional probability comes from conditional expectation. What is conditional expectation? It's easier to see if you think of the expected value also being as projection. So you have the constants and the rest, which has expected value 0, and it's a projection onto the constants. Okay, so the function 1 times its expected value. And what Kolmogorov says, it's the conditional probability is also a projection. It's a projection onto a space in L2, that's the simplest one, on a space with a subsigma algebra. Okay, and then I have an orthogonal decomposition of my whole space. And the conditional expectation as an operator is just the orthogonal projection onto this guy here. Okay. With this, I know it minimizes the distance squared Bayesians would call this a loss function, okay? And it satisfies these Galerkin conditions, orthogonality conditions. We know the orthogonal projection is orthogonal on the subspace. And this can be used numerically. I mean, you can start doing numerics right away. You can compute the conditional expectation with Galerkin methods, okay? We're just discretizing this equation. And so how does the whole thing, this is how it was for random variables, okay? So how this is defined for probability algebras, where we don't look at sub-sigma algebras, we look at sub-algebras. So if we have an observation, we look at the algebra generated by this observation, okay? And then we look at the Hilbert space, which is the closure of that algebra. That's the closed subspace of a Hilbert space. So we have an orthogonal projection. That orthogonal projection is defined to be the conditional expectation, okay? And I have the same formulas as before, okay? So the idea is now the conditional expectation defines a new state. My interpretation is my state of knowledge has changed through the additional information, and this is why I have a new expectation function, okay? So I get a new state, which is exactly this here, and the whole game starts from the beginning, okay? So the Bayesian updating essentially is a change of the state. Okay, so let me conclude. I hope I could at least show a little bit that these weak probability distributions, they are more general than the strong ones, and they can be defined via linear maps. That's a really nice feature, okay? That we can use the covariance, even if it's an unbounded operator, whatever, you can use the spectral decomposition and the decomposition of the covariance to do different parameterizations. Okay, then I hope I could show you a little bit the probability algebras. You can do probability theory without measure theory. Okay, the expectation becomes a central object. Okay, there's a strong connection with spectral theory. We can use duality theory to define wild random variables, and we can do Bayesian updating. That's the end. So thank you very much for your attention.
Questions?
Yes.
Last week when Michael Goldstein was here, he talked about Bayes linear
Right.
methods which use expectation as the primitive
Right.
rather than probability.
Right.
And that seems rather similar.
Yeah, it's very
to what you're
similar.
doing
So,
here.
but what the additional thing, what he has done is, so see, the conditional expectation here being orthogonal projection,
Yeah.
but if you view it as a function of the observation, is a map. And in Bayes linear, you make this map linear. So you take a linear approximation. So this is what, and that's the simplest way of approximating this. Okay, and the Kalman filter is an example of this and whatever. But it's exactly this kind of idea. Yeah. That's right.
Anything else?
If I understand this correctly, at the very beginning, you define everything in terms of the projections from bigger space to a smaller space.
You mean for the expected conditional expectation?
Yeah. So
Yeah.
would that depend on the choice of basis vectors you project onto for big spaces that you project down from?
So you mean now for normal probability theory, the way Kolmogorov defined it, or what? It does not depend on the choice of basis. So this is completely independent of basis. Okay. So Kolmogorov says we take as the sigma algebra the one generated by the observation. Okay, that's a smaller sigma algebra than you worked beforehand. You look at the L2 space with that sigma algebra. That's a closed subspace, and you take the orthogonal projection onto that subspace. That's what he defined to be conditional expectation. And you can show in the cases where the other formula works, it gives the same thing. Okay, but it's completely independent of any choice. Of course, when you start computing, you have to choose basis and things like that. The definition has nothing to do with any choice like that. You don't need any basis.
Thank you, Hermann.
Thank you very much.